Hello everybody! In this clip we introduce the Cox sheaf, the Cox ring. We take a look at the example of a toric variety and we discuss algebraic properties of the Cox ring. Let us enter the construction of the Cox sheaf and the Cox ring. X is a normal variety. We assume that every invertible global function is constant on X and that X has a finitely generated divisor class group. The latter allows us to find a subgroup K of the while divisor group, mapping surjectively onto the divisor class group. Take a look at the sheaf of divisorial algebras associated with the subgroup K. In the torsion-free case, we can manage that K maps isomorphically onto the class group, so our divisorial sheaf S can already be considered as the Cox sheaf. As soon as we have torsion in the divisor class group, there is no chance that this map will be an isomorphism. In this case, our sheaf S is too big in the sense that it has isomorphic homogeneous components. And the idea is to identify these isomorphic homogeneous components of S in a systematic way. For this, look at the kernel K0 of this homomorphism. Then we can choose a homomorphism chi from K0 to the multiplicative group of non-zero rational functions of X in such a way that the divisor of chi of E equals E itself for all the divisors E from the kernel of the projection map C. Using the homomorphism chi, we can define a sheaf of identifying ideals in S. It is generated by the elements 1 minus chi of E, where E stems from K0. So it identifies the element 1, living in degree 0, with the element chi of E, living in degree minus E. The Cox sheaf of X is the quotient sheaf S mod I. By construction, this quotient sheaf is graded by the factor group K mod K0. But this is just the divisor class group of X. So our Cox sheaf is graded by the divisor class group. The homogeneous component of degree class D is the image under the projection of the direct sum of all homogeneous components of degree D prime, where D prime has the same class as D. So this is the way we identify isomorphic homogeneous components of our sheaf S. The Cox ring of X is the algebra of global sections of the Cox sheaf. The assumption that X has only constant global invertible functions made in the construction of the Cox sheaf and the Cox ring is to ensure that these objects are unique up to isomorphy. Let us look at the example case of a toric variety. Being a toric variety, Z comes with a torus action, having a big open orbit, and apart from this orbit we have the boundary, which is a union of invariant prime divisors D1 up to dr. The classes of this boundary prime divisors D1 up to dr generate the divisor class group of our toric variety. And now it is fairly easy to write down the Cox ring of Z. It is a polynomial ring in as many variables as we have invariant prime divisors. And the degree of the variable ti is the divisor class of di. Things can be made more concrete if our toric variety is given by a fan sigma in a lattice n. Let V1 up to Vr denote the primitive generators of this fan, that means the primitive lattice vectors inside the rays of the fan. Define a linear map P going from Z to the R is the number of primitive generators, to N, sending the ith canonical basis vector to the ith primitive generator of sigma. Then with dual map, the divisor class group is the co-kernel of this dual map. With projection from ZR to the co-kernel, the Cox ring can, again written down explicitly, it's a polynomial ring in the variables t1 up to tr, and the degree of the ith variable is the image of ei under Q. We discussed general properties of the Cox sheaf and the Cox ring. So look at the right. The X with Cox sheaf are given as a quotient of a sheaf of divisorial algebras S by a sheaf of identifying ideals I. First observation is that the projection map P from S to R induces isomorphisms on the homogeneous components. The second thing, for any open subset of X, the algebra of sections of the Cox sheaf over U is the quotient of the algebra of sections of S by the sections of the ideal sheaf over U. This is not a general feature of quotient sheaves, it is a particular nice feature of our Cox sheaf. The next aim is to associate a divisor with any homogeneous element of the Cox ring. So look at the variety X with a Cox sheaf R given as S mod I, and a homogeneous element of degree class D in the Cox ring. Then F is of the form pi of F tilde with a section F tilde of degree D of the sheaf of divisorial algebras projecting onto the Cox sheaf. This we use to define the class D divisor and the class D localization of the homogeneous section F of the Cox ring. The class D divisor of F is the divisor of the representing section F tilde plus D, the degree of the representing section F tilde. The class D localization of F is just X minus the support of the class D divisor of F. Here's the first statement on algebraic properties of the Cox ring. The Cox ring is always an integral normal ring. Moreover, if we have a homogeneous section, then the localization of the Cox ring by this section is the algebra of sections over the class D localization of F. Second statement concerns the units. Every homogeneous unit of the Cox ring is constant. Moreover, if the variety X has only constant global functions, for instance X is complete, then every unit of the Cox ring is constant. We come to divisibility properties of the Cox ring. What we need are homogeneous versions of the standard notions. So consider a C algebra which is integral and graded by an abelian group K. A homogeneous, non-zero, non-unit f of R is called K prime if it satisfies the following. Whenever F divides a product of two homogeneous elements, then it divides one of the factors. The algebra R is called K factorial if every homogeneous non-zero non-unit is a product of K prime elements. If the grading group is torsion-free and the algebra is finitely generated, then the notions of being K factorial and B factorial, that means unique factorization domain, are equivalent. The following proposition interprets divisibility in the Cox ring in geometric terms. Consider homogeneous elements F and G in the Cox ring of degree class D and class E. Then F divides G if and only if the class D divisor of F is less or equal to the class E divisor of G. Moreover, a homogeneous element of class D in the Cox ring is CLX prime if and only if the class D divisor of F is a prime divisor. Here's the final statement about divisibility in the Cox ring. Consider a variety X, this Cox ring R of X. Then the Cox ring R of X is CLX factorial if the divisor class group is torsion-free, then the Cox ring is a unique factorization domain in the usual sense. See you in the next clip.